See, I wrote in the board some reminders from last time. It's a reminder of the definition of finite dimensional algebra being twisted equals to periodic with respect to a given algebra automorphism. It means that the algebra given as a bimodule itself has a d plus second syzygy that is isomorphic to the bimodule, the diagonal bimodule twisted on the right by the automorphism sigma up to projective summands. Also throughout, we will, whenever triangulated categories appear, they will always be essentially small, k-linear, finite, and Kuhn-Schmidt. So yeah, if I forget to say this, it's always in the background. And objects are often assumed implicitly to be basic, even if I forget to say that. This means when I decompose them into indecomposable summands, there is no repetition among the indecomposable summands that appear. Also remind you now of the main definition that we are interested in. So given such a triangulated category and a basic object in it, we say that this object is dz cluster tilting for a positive integer d if it's isomorphic to its default shift in the triangulated category T, and the additive closure of T can be described simultaneously in two additional ways, namely in terms of vanishing of self-extensions, extensions by or from T in a certain range, so between 1 and d minus 1. Yeah? So this is the concept that we are most interested in, and we have seen that these cluster tilting objects allows us to describe a triangulated category and using iterator extensions in a very nice way. In particular, they are what are called classical generators of the triangulated category, so the thick closure of T is curly T. So in a way, we're interested in classical generators of triangulated categories with a very distinguished property. And when we concluded last time by this proposition, due to Dugas in the algebraic case, to Hanihara in the case equals to 1, and to Chan, Darpo, Iyama, and Marcinsek, whose name I sadly forgot to write last time, in general case, and I explained using some other results of Geisler-Oppermann an independent proof that leads us to this result using the triangulated categories. That tells us that if I have such a generator of T called dz cluster tilting, then its endomorphism algebra, that is a finite dimensional algebra by virtue of the home finiteness assumption, is then twisted d plus 2 periodic. Yeah, so this is a brief summary of what we did, or parts of what we did last time. So what I explained is that now I would like to understand in which sense is this implication reversible. You know? So, but before that, I want to point out that we know actually quite a lot more about, how the endomorphism algebra of T relates to its graded endomorphism algebra. So recall that the graded endomorphism algebra of an object in a triangulated category is just the sum over all homs from T to its shifts in positive and negative directions. So now T, of course, belongs to its additive closure. So it has no self-extensions in degrees strictly between 0 and D. And by virtue of this isomorphism, actually there are no self-extensions in any degree that is not a multiple of D. So this is actually just the sum over all di's multiples of D on T shifted by di. So now you see here why the name dz cluster tilting is reasonable. Its graded endomorphism algebra is concentrated in degrees that are multiples of D. It's meant to remind us of this, and the cluster tilting property is related to this resolution type property. Okay? So that's very good. This algebra has a multiplication given f is the obvious thing, f of degree I, and then g of, let's say f has degree j, and g has degree I. Then I want to multiply F and G, and of course these don't compose, but I can just shift G by J. So I can define this to be G shifted by J after F, right? So that G has now domain T shifted by J, and then I can compose using the composition law in the triangulated category T. So another thing I want to observe is that, well, I can choose an isomorphism between T and its default shift, because this is part of the existence of such an isomorphism, is part of the definition of being a D-set cluster tilting object. And then I can define an algebra automorphism that depends on phi of the endomorphism algebra, the ordinary ungraded endomorphism algebra of T. And well, what does it do? So let's see. So if I have something from T to T, let's say yes, to T, let's say F. Well, what I can do is I can use phi to go to T shifted by D. Then here I can take F shifted by D, and then I can okay, well then I'm still T shifted by D, and then I can take the inverse of phi, and then I get here something that I would call sigma of X. So one can check this is an algebra automorphism of this algebra, and it will exhibit, it's related to this twisted periodicity thing that we need. But what I want to point out about this is that I can write the graded endomorphism algebra, so the of T that now has well, an invertible element of degree D in it, namely this automorphism phi, as effectively a twisted log polynomial algebra that will denote n T sigma D, defined as adjoining to T, sorry, to the endomorphism algebra of T, an invertible variable by some convention of degree minus V, so represented what is essentially phi inverse, but I need to normalize because of the form of this thing, modulo the relation that IF is equal to sigma F I for all F in this endomorphism algebra. So one can check that there is an isomorphism of graded algebras. So what I see now is that if I know that I have a D-set cluster tilting object, I essentially know, if provided I can compute this and the action of such as phi and then therefore sigma, I know the whole graded endomorphism algebra of T completely. Yeah, so that's one thing I want to point out.
Is I the degree of F?
The I?
The I in the I field. The I in the I field of the.
I'm not sure where you're. Can you come back here? I'm not sure where you're pointing.
The I F minus delta X.
Minus sigma is the action on it. So this is not a commutative variable. It kind of sigma commutes with things. Yeah.
Right.
So that's why it's a twisted Lagrange polynomial.
Right. Yeah. Algebra.
Okay, so that's very good. So basically, from the data of this endomorphism algebra in sigma, I can recover this whole graded endomorphism algebra. And of course, you can imagine that up to an isomorphism, because of this side is independent of sigma, this will turn out to be independent of sigma. So this is some bookkeeping. So here I write phi minus after ft just for completeness. Okay.
Is the endomorphism algebra like formal? Like, are we losing information when we're defining it as?
Well, we haven't introduced any higher structure, so we haven't lost any information. We didn't have any extra information. We have, but this is indeed just a graded algebra, so it has no differential. But we haven't assumed yet any enhancement on T. So as of now, we have not lost any information. So this is, in fact, I want to point out that all the information that we could ever get about this gradient endomorphism algebra, we can get just from the degree 0 part and this sigma. Yeah, so I need to remember a little bit less in order to reconstruct this graded algebra. That's the summary. Okay. So now, with this in mind, I want to move on to the nicer the works already. I want to move on to the next section. So the next section is the derived Auslander Iyama Correspondence. So I will now, as fast as possible, present one of the main theorems of this lecture series. But first I need to do some reminders. So first, recall that we will work over a perfect field. This is a technical reason that I will hopefully, maybe I will succeed to explain where it is used, but you can just think of an algebraic calculus field or a finite field or a field of characteristic zeros. So some situation where everything is you're familiar with and everything is fine. It's just a technicality can be safely ignored. And now, in order to reverse this implication, I'm required to construct a triangulated category, first of all. And in general, as we all know, triangulated categories have their shortcomings. And in particular, it can be difficult to construct triangulated categories with given properties. So at this stage, we are forced, essentially, to accept that T needs to have some form of enhancement. And because of the context we will be working in, like the examples that we're interested in and so on, this enhancement will be given by the DG category. This is our choice, and this is what we're going to do. So we basically want to control our category with DG algebras. So given a DG algebra, I remind you that this is not small, but I can take the derived category of A, and inside this I can take the thick closure, the thick subcategory generated by the free DG module of rank 1, and this is this turns out to be the full subcategory. So this is a compactly generated triangulated category, and these are precisely the compact objects, and this subcategory of compact objects is called the perfect derived category of A. That almost starts to satisfy some of these assumptions. For example, is idempotent complete. Now, we will later then put some home finiteness assumptions, but then I want to remind you of a simplified version of Keller's 1994 recognition theorem. So T is essentially small, K-linear, and idempotent complete. And then I have an object such that the thick closure of G in T is everything, so it's a classical generator. Then T is algebraic. So you know what algebraic means, it doesn't matter. This is equivalent to the existence of a DG algebra A over K, of course, an equivalence of triangulated categories between C and the perfect derived category, so T and the perfect derived category of A, that exchanges T and A. Yeah? So, in other words, in the context we are interested in, so cluster tilting objects fit in this recognition theorem. Once I assume the ambient triangulated category to be algebraic, we can actually rather work with perfect derived categories of DG algebra. So now we make our problem more concrete. Yes, sorry, I was going to change my mind in then that's not a good idea. Thank you. G was G and A. Yeah, so our generator. So I will try to keep T for cluster tilting. Okay. And moreover, in this case, it follows, because an equivalence of triangulated categories, that the graded endomorphism algebra of G is isomorphic as a graded algebra to the cohomology of A, because the cohomology of A can be seen as the graded endomorphism algebra of A in the derived category. Yeah? So we have that. So instead of working with this, we now work with the G algebras and their cohomology. Very good. Now, the main theorem that I want to present first, which is not written exactly in Fernando's paper in this way, but you can easily sort of rearrange the results in this form. In the case D equals to 1 of additive generators, and in our joint work, in general, is, so I try to motivate this theorem, so I hope I didn't give you a misleading impression by discussing so much about the classical Auslander Iyama correspondence. The idea of that discussion was to motivate the form of this theorem and to explain to those of you who are not representation theorists of finite dimensional algebras why in our subject people could potentially be interested in a theorem of this form. Yeah? Because it's a theorem maybe presented in a form that maybe is not common in other fields, so to speak. Okay? So the statement is that there is a one-to-one correspondence. That's why it's called correspondence. It's going to look like the Auslander Iyama correspondence is derived because it's about the derived categories. Okay, so we're not that creative. Yeah? So between the following. So on the one hand, we have quasi-isomorphism classes of DG algebras A with the following two properties. First, because I want to work in this whole finite setting, the cohomology of A is degree-wise finite dimensional. This is an important assumption for us. And B, well, the perfect derived category of A has a canonical classical generator, the free digimodule of rank 1, and I will ask that this generator is this set cluster tilting. Now here, I'm fixing a positive integer. Everything is now relative to this fix. Yeah? So the second class of objects, so this instead of in the classical Auslander Iyama type correspondence, you can also write it in a different way, so it looks more like this, but there were only two classes of objects, right? So finite type algebras or algebras with cluster tilting module corresponds to some higher Auslander algebra, so with global dominant dimension conditions. Here there will be three classes. So here is equivalence, so the second class is equivalence classes. Of pairs T comma T, where A T is, and I really should have given it a name, but and I probably will. Yeah. Sorry. T satisfies star. And is algebraic. And B, T is an object of curly T, which is this set cluster tilting. So there will be a third item in the theorem, but the correspondence from 1 to 2 should be pretty clear. I take a DG algebra and I send it to the pair consisting of its compact derived category or perfect derived category, so I mix up always these two terminologies. in my mind, together with my given Lizard cluster tilting object, right? So this is not very hard to see that it's well defined. Right? Now I will make some comments, maybe now before adding the other terms. So notice here that there is no uniqueness statement about this DG algebra, because at the level of this equivalence of triangulated categories, I really can only see the cohomology of the DG algebra. So I don't have access really to A. Yeah, so it's not somehow a consequence of Keller's theorem that there is a bijection between 1 and 2. Yeah, because here is a statement about triangulated categories. So this T is enhanceable, right? But it's not enhanced. Enhanceable. Okay, so this is here from 1 and 2, and then there is a point 3. So equivalence class of pairs here should be clear what it means. Are equivalence of triangulated categories that send an object to the other, right? This is a natural thing. And then I have equivalence classes of pairs, lambda comma sigma, where A lambda, so remember for us, Lizard cluster tilting always means basic, yeah? So basic, well, just, I will forget to say it all the time, but always it is. This is a basic finite dimensional algebra, which means when I decompose lambda as a finite direct sum of decomposable projectives, none of these projectives appear with multiplicity higher than 1. That is self-injective. Actually, something I didn't mention that I will mention now is that twisted periodic algebras are automatically self-injected by a theorem of Green, Snashel, and Solberg. So if they have finite global dimension, they are semi-simple, and otherwise they have infinite global dimension. So this is kind of orthogonal to the class of higher Auslander algebras that appeared yesterday. So this is some condition that will need to be satisfied anyway. And B, sigma is, well, an algebra of homomorphism of lambda such that lambda is twisted d plus 2 periodic with respect to sigma. Now the correspondence between 2 and 3 is probably, hopefully not surprising. If I take a pair consisting of an algebraic triangulated category satisfying star and a Lizard cluster tilting object, I'll send it to the pair consisting of the endomorphism algebra of T that I know by virtue of the proposition that it is twisted d plus 2 periodic, and sigma is sigma phi for a choice of phi isomorphism between T and its default shift. That exists because T is assumed to be Lizard cluster tilting. And here equivalence classes of pairs means that you should think, so maybe second remark, from the pair lambda sigma, one produces the pair consisting of the category of projective lambda modules and an autoequivalence given by, let's say, let's choose this special bimodule that appears in the definition of twisted periodic. So this becomes a category with an autoequivalence. So two pairs are equivalent if the corresponding categories are equivalent. Yeah? So basically what I'm trying to fix here is, as you will see, something like the action of the default suspension or its inverse on this category.
Gustavo, you said that these twisted D plus 2 parameters are automatically self-injective.
Yes.
Why is it in the statement of A?
Where it is what?
Why is it in part A that you require this thing to be? Is this needed?
Yeah, it's just to have it in mind. I mean, it's just like to make it the point that it's a self-injective algebra that is actually twisted period. Yeah. Sorry, what I wanted to say now. Right. Okay, so that is the theorem. Moreover, the triangulated categories in 2 admit a unique DG enhancement. So now I want to comment on this theorem. So well-definedness at every stage is now hopefully clear. And by reversing the implication, I mean I will now focus on the correspondence from 1 to 3. So if I go all the way from 1 to 3, here I will have the zero cohomology of A and some sigma. And in this case, and maybe it's useful to mention that this twisted bimodule is going to be isomorphic as a bimodule to the minus d cohomology of A. So an alternative way to write this would be to choose instead of sigma a suitable invertible bimodule over lambda. And here the invertible bimodule that I will get is the minus d cohomology of A. So basically, if I remember the zero cohomology of A and the minus d cohomology of A as a bimodule over the zero cohomology, that turns out to be enough, which is very surprising because this is a statement about quasi-isomorphism classes of DG algebras, and these are now higher structures. And I want to reduce the problem of checking this quasi-isomorphism to checking something at a very non-higher structure level. Yeah? So basically isomorphism of algebras together with a choice of specific invertible binomial. Yeah? And so that's already somehow surprising. So reversing the implication corresponds to the surjectivity of the map from 1 to 3. Right? So if I can go back from 3 to 1, I will build this triangulated category with a decent cluster tilting object whose endomorphism algebra going to go back to this. So take a pre-image, then we'll go back to the original twisted periodic algebra. But of course the theorem does at the end even more, and this was personal. So I was already surprised by Fernando's work in the case d equals to 1. He was thinking about this as a result about uniqueness of enhancements. So this is the surjectivity is a statement about the existence of enhanceable triangulated categories, if you want. And I mean, the fact that even in general D is still a result about uniqueness of enhancements, I think it's interesting because typical results about uniqueness of enhancements use existence, for example, of these structures or some way to sort of spread around your objects in the category. Whereas, for example, already for d equals to 1 in a finite triangulated category, I don't have non-degenerate D structures. So I leave this to you to think about if you have not thought about that before. So this is a uniqueness of enhancement theorem of a different sort. But we also like to present it in this way, perhaps at my request, because I was very influenced by the work of Auslander and Iyama since I began my career. So these type of theorems are very sort of easy to parse for me. Yeah, I understand like what the theorem somehow means, but this maybe, yeah. Okay. So this is the theorem I want to talk about. Okay. So
one question. In the case of d is equal to 1, Fernando was proving the uniqueness of enhancement essentially. How did we come up in his story?
Who came up?
No, d equal to 1. Why do we need 3 in the case of d equal to 1 if we're only interested in d?
Yeah. Why do we need 3? So he was also looking at twisted periodic algebras. Yeah, this was. Yeah, it came from the story of these amyot triangulations and so on, twisted periodicity. So it was already in that case. Yeah. Thank you for the question. Now, yes. So what we see here is that, for example, to prove surjectivity, I need to understand how from this kind of data, like a twisted periodic algebra and an automorphism sigma, witnessing that fact, I can produce a DG algebra. And in the end, we actually will not produce a DG algebra. I kept just saying DG algebra all the time until now. But what will turn out is that we will need to construct a minimal model of the DG algebra that we want as a minimal A infinity algebra. This will be much better. I will explain why at some point. Now, before continuing and discussing other, maybe at some point I will give some list of examples, but I have a feeling that maybe for a lot of you, maybe the techniques of the proof will be more interesting than the example, more enlightening than the examples. So there is a definition. So this is a first theorem. And now I can play a game. I want to understand more things. So I can add properties to the DG algebras in one. So I can restrict to a subset of the domain, and I can try to understand the image. Why not? I guess. So there is a definition used in Kontsevich, 1993. It's appearing in notes of Kontsevich and Zollerman. In 2000, some number. Let's write. So I wrote it down. 9. In my BibTeX file, the citation key is wrong. I remember the wrong name. So we take A to be a DG algebra, such that the cohomology of A is degree-wise finite dimensional. So we say, so this notion comes from, motivated by the name algebraic geometry. I don't have time to explain too much, but you will see it's a very natural definition from an algebraic perspective as well. We say that A is bimodule right and Calabi Yau related NCY if A shifted by n is isomorphic to the dual of A in the derived category of DGA bimodules. So here D is not the dual from last time, the naive vector space dual. This is the DG dual. So apply to the degree, homogeneous degree components and degrees, and so on. Yes? So you see that this is some kind of notion of like shifted symmetric. Yeah? So symmetric algebras are those algebras which are isomorphic to their duals as bimodules. This is something like shifted symmetric. So from a derived perspective, this definition is very natural. So there is now a proposition that is follows from this. So if A is a bimodule, maybe I make a remark for those of you that know things about this. So there is a notion of a right n-Calabi Yau structure, and this is a weaker definition. Sometimes the existence of such an isomorphism may be called a weak right n-Calabi Yau structure. I say bimodule instead, but there is a refinement of this definition that will not appear in this lecture series. If A is bimodule right, and this also because there is right, there is left, right? So I will not explain what left Calabi Yau is, but this is a notion for homologically smooth DG algebras. You know about this, you already know, I think, anyway, what I meant to imply by all. So if I have A by module right Calabi Yau DG algebra, then the following statements hold. The perfect derived category of A is confinite. And this is a reason why representation theorists of algebras would be interested, for example, in this kind of property. This is really a property because it's just about the existence of such a bimodule isomorphism. The shift by n with its standard triangulated puncture structure is what is called the graded Serre functor. So graded just means you need to take care of some signs, and Serre functor means that the natural form of Serre duality is satisfied, so that there are isomorphisms of vector spaces natural in X and Y of the following form. So if these are just natural in the sort of vector space sense, you just have an ordinary Serre functor, and the grading has to do with compatibility with the action of the shift in the signs. let's ignore this for a second. So that's very good. Another comment maybe I write here quickly. Of course, I can pass to cohomology, working over a field, and everything will be very nice and simple. So I have that the cohomology of A is isomorphic as bimodule over itself to its linear, so digilinear dual. Okay. As graded bimodules. Okay. So I have some properties of such digi algebras. So the first thing I see is that, of course, they satisfy, for example, these whole finite full Schmidt assumptions of the derived category, so they start to fit in this context. So I can add that property to the theorem. So it's a good question. What should I know? So this is what I will not explain is a certain formulation of a more recent theorem. So it's a refinement in the sense that it's under more assumptions. We still understand correspondence. This one not very good. So this is a more recent theorem. Here in the archive this year. So let's take, so we still have d greater than or equal to 1, m an integer, and m times d. You will see where this comes from. So let A be a dg algebra such that H star of A is degree-wise finite dimensional. B, the rank 1 free digit module, so the free digit module of rank 1 is a Bissell cluster tilting object, basic. Is a cluster tilting object in its own compact or perfect derived category. So I am in the setting of collection 1 in the Derived Auslander Iyama Correspondence. And then I will assume that there exists a bimodule isomorphism, graded bimodule isomorphism, as it would need to exist if this dg algebra would be bimodule right Calabi Yau, right? So this is a necessary condition for A to be bimodule right Calabi Yau. Now here you see, because H star of A is concentrated in degree multiples of D, and D only flips the degrees. This is still concentrated in degrees multiples of D. This without the shift is concentrated in degrees multiples of D. If they are bound to be isomorphic as graded modules, I can only ever shift this by a degree that is multiple of D. Okay? So there is no mystery why this is necessary. Could have put an N and it would be implied it's on this form. Right, so I have this graded bimodule isomorphism. Now the statement is that H star of A, no, not C star of A, sorry, A is bimodule right and Calabi Yau. And then the way I want to write this is in a way that it's not supposed to, when I write something, you're not supposed to necessarily understand it. Okay? This is, it's the point. So don't be surprised if you wonder what happened here. Like this what you're following, and then something happened, and some symbol appear. Okay, sorry. Yes. So here I'm doing this as a graded algebra. So there is a vanishing of a certain thing under a certain operator. Yeah, there is some condition. So where HH star of this means the Hochschild cohomology of this graded algebra. So for those of you who are already thinking about the minimal model of the cohomology, this is without this structure. It's just as a graded algebra. It inherits a bigrading, so it is now a bigraded thing. This is a class of by degree d plus 2 minus d on this Hochschild cohomology, which is called the universal Massey product of length d plus 2. I'm sorry for the long name. And delta, that depends on the choice of this phi, is the so-called battalion Minkowski operator induced by the existence of such an isomorphism and doing some trick related to the B operator and Hochschild homology, but some kind of work to that. So I wanted to present this theorem because, well, yeah, it gives us now more information. It tells us that somehow this is not the end of this kind of story, that one could, well, add maybe other conditions, but one thing I would like to advertise is that one could look of theorems of similar form, yeah, so where one can uniquely determine the quasi-isomorphism type of a DG algebra or a ring spectrum or whatever you're interested in by what we without defining what this means, by a very small amount of data, yeah, that is not so higher structure necessarily, right? And there is no precise definition of what what such a theorem should look like, but this is some kind of example, yeah. And here you see that, well, the more conditions that you, or properties or structure even maybe you might want to impose on your DG algebra or perhaps ring spectrum, maybe more and more invariants might need to be considered. Now, another reason I wanted to present this theorem anyway, so I wanted to maybe talk a little bit about the proof of this theorem as well, but I will focus on the proof of the first one and see how far we get with that. Both proofs are actually long, so yeah, this is just talking about that theorem is a challenge. But, well, many of you probably know Hochschild cohomology, maybe also Hochschild cohomology of graded algebras. We will do a brief reminder as it becomes necessary. As it turns out, this universal Massey product already plays a role in the proof of this theorem, both for the surjectivity and the injectivity. And, well, this battalion Minkowski operator, its appearance is new, it depends on phi, so it couldn't have appeared before. But it's just maybe for those of you who know what these things are, that you can see maybe something that resonates with things that you know or perhaps even interested in. So I have about 15 minutes? Yes. Right? Yes, very good. Right. So maybe I would just say in words examples of triangulated categories that fit within this correspondence. So for d equals to 1, one has stable modular categories of self-injective algebras of finite representation type, cluster categories of Dynkin quivers, as explained by David. One also has, for example, certain triangulated category structures on categories of projective modules over preprojective algebras of Dynkin type. This is work of Calabi Yau, for example. For d equals to 2, one has stable categories now of not projective models, but stable categories of preprojective algebras of Dynkin type AN, cluster categories of self-injective quivers with potential, cluster categories of weighted projective lines. And well, there is a particular example that is of interest. So there is a so-called singularity category of an isolated compound of odd singularity with a Crepin resolution, for those of you who have heard of this. So there was a conjecture of Donovan and Wemyss about these kind of singularities that are of interest in the homological minimal model program for threefolds of Michael Wemyss. And the main theorem provides the last step in the first proof that appeared of that conjecture, something that was pointed out to us by Bernard Keller very kindly. For d equals greater or equal to 1, there are more and more examples. So in representation theory, and let's call them nearby fields, whatever nearby means, I can choose. So there are many examples, and now in general, what this permits is, for example, to detect equivalence of triangulated categories by checking some properties. So as you can see, the existence of a D-set cluster tilting property object is very strong. Before I continue, let me make another remark. So I erase the definition of a cluster tilting module, but maybe I write this as a remark here. Notice that T in T being D-set cluster tilting only depends on the pair consisting of T and its shift. Because, so I don't need a triangulation, because to know, so the condition was T isomorphic T shifted by D, so only uses the shift, and the condition on vanishing of extensions is just homes into shifts, So it doesn't actually use a triangulated category structure. And this, together with this strong symmetry, maybe it's one reason why, if you have thought about these cluster tilting objects a lot, you could expect such uniqueness of enhancement result to be this is another comment. Are there any questions up to here?
Yeah, I was just wondering if this is completely random, but because the base is one, and then we have three twists.
Twist three periodic, yes.
And then I also feel like the triangulated structure is encoded in the lower three message products.
Yes, that's absolutely correct. That's right.
So that's sort of why.
Yeah, this is all related to the actual proof of the theorem. So thank you for the remark. So the remark here was that in the case equals to 1, there is something about twisted tree periodicity, and there is some kind of M3 there. So for those that you know, this M3 has to do with this triple massive products, and there is something about understanding the interaction between this M3 and the triangulated structure in T and the condition of being twisted tree periodic. And I mentioned before that one way to prove, so that was yesterday, one way to prove that endomorphism algebra, so these cluster tilting objects are twisted D+2 periodic, was showing that the additive closure of T has a D+2 angulated category structure. So now understanding the relationship between that D+2 angulated category structure, the triangles in T, and this Heidegger operation. I mean, if you know infinity algebra, you see the form this is immediate, this is reminiscent of a Heidegger operation, plays an essential role in the proof. Okay, So I have 10 minutes, and with that, I will need to erase this, and now I do this. Yeah, so while I erase, let me emphasize, so something I've noticed whenever I talked about this topic is that very often the role of this algebra automorphism sigma is not clear, perhaps because I don't explain it very well. And what it does for us, it encodes. So I wrote that here this pair. You can instead think about the pair additive closure of T and the default suspension, which now acts on this because T is isomorphic to its default shift. And sigma gives a sort of minimal way to encode that autoequivalence by an algebra automorphism. And this is somewhere where we leverage that we work with basic objects. Yeah, so if you are confused about that, then that's similar to the role played by the bimodule h to the minus d. So that one corresponds, well, both sigma and its inverse can be used at the same time to encode, maybe to match up with that pair above. This is technically minus. If I put the sigma on the other side or a minus on the right, then it's then positive shift. So basically, I just want to encode some underlying additive category and a suspension and relate this to this higher angulations. Okay. So the next thing is about the relationship, very briefly, how to go from, well, I will not explain how actually to go, from DG algebras to A infinity algebras. I might say something maybe with more detail tomorrow, but maybe I will explain the following. So there is a theorem.
So is this section 3 or 4?
I don't know, you tell me? 3. Section 3, thank you. There is a theorem, Kadeshvili, that says the following. If I have A, DG algebra, over my base field K, then the graded algebra given by its cohomology, will write inherits a minimal A infinity algebra structure given by a collection of maps. Sorry, let's call this guy, let's not call it anything. So a collection of multilinear operations of arity n, single output, and degree 2 minus n, n bigger than or equal to 2. So there is a notion of an A infinity algebra that is not minimal. This means that M1 is 0. M1 is a differential in an A infinity algebra, and then in the case of the cohomology of a DG algebra in general, there is no natural differential, so this is not unexpected. And well, for n equals to 2, this is a binary operation that corresponds to the binary operation of the graded algebra H star of A, satisfying some equations called the infinity equations. I will not write down these equations today. Moreover, this minimal infinity algebra structure is suitably unique. So it's not unique, but it's unique in a good enough way. And so there exists what is called an A-infinity quasi-isomorphism. I know I'm saying a lot of things that maybe don't necessarily make so much sense right now for those of you who have never seen this, between A and its homology equipped, where this is equipped with the minimal A-infinity algebra structure. So the upshot of this is that A-infinity algebras also have derived categories, and the derived category of this minimal A-infinity algebra, so I'm going to write, let me write these operations as MA because they are induced by A. Yeah. And then there are some choices, so those that you know, and if not, there's unfortunately no time to explain how this is constructed. It's very combinatorial after you're giving some choices, it's very nice, but there is no time. So this is equivalent to the derived category of A, strangulated even as enhanced strangulated categories as well. So in particular, instead of looking, so that means if A is this, and it exchanges, of course, H star of A and A. So if A is this cluster tilting in the perfect derived category here, then the same is true for its cohomology as an infinity by modulo over itself. So in other words, I can use this to, instead of working with DG algebras, to work with these other objects that I will define next time, because I realize that there will be before there will be no time to get into detail to this. I will explain what these equations are, but what this equivalent presentation of this highly structured object does for me is that it reveals the existence of these other operations. Yeah? A DG algebra is an A-infinity algebra with vanishing higher operations for N3 and higher. Yeah? So, as you can see here in the theorem, and one of the main ingredients is this universal massive product of length d plus 2. If d is equal to 1, so d plus 2 is at least 3. So I wouldn't be able to see this class, which is an important invariant that we will discuss next time, if I work with the DG algebra. But if I instead look at this equivalent, so this means that the quasi-isomorphism type in the correct context of these two objects is the same. This object, it's much smaller because it's just the cohomology of A, has no differential, but all the homotopical information of A is now unraveled in these higher operations. And I have, so the way I like to think about it is that now I have access to these additional operations and I can study them with use, of course, of this same, you will see why these infinity equations now play a role. So I have some more operations and some explicit equations that I can look at in order to understand this kind of invariant. So with this, we will continue next time.
Any questions for Gustavo?
So here, your base, does it need to be a field or is like global?
Yes, no, it's important that you need to be able to construct a deformation retract of A into its cohomology. So you need some splitting. So you need some assumptions for this to
Is global dimension 1 enough? Is over 0?
I guess you still will need some projectivity assumptions. Yeah. But yeah, so we are safe. We're a field, so everything is sort of all those obstructions are true. Yes, David.
Does something interesting happen if I take A to be a finite dimensional algebra?
Sorry.
Does anything interesting happen if I take A to be a finite dimensional algebra and use this theorem?
No, because of these degrees, all the higher operate. So there is the cohomology is just A, and there is no more inheritance thing. It just collapses. So I mean, for n equals to 3, this needs to be 3 minus 3 minus 1. So you need degree minus 1 maps, and then but there's nothing in degree minus, so you can't. Are there any other questions?
Yes, I have a question. So you say so via this equivalent you get access to some information, this M3 for example, if this one.
Yeah.
Which you can now some kind of obstruction that you get. Is there no way of interpreting that somehow on the right hand side in DFA, so not as M3 which will vanish, but something else maybe?
You can relate it to the massive products of the digi category, so of A and of the digi category of the digi derived category. So you can relate it to that. You can relate it to the toda brackets of the underlying triangulated category. But as the way we will need it, I don't think you can really see this in a very good, clear way from the DG perspective. Yeah. That's my limited understanding.
Any other questions? Okay, let's thank Gustavo again.